let us go to the Aspen Plus window. So this is the Aspen Plus window. So we have to define the biomass, but before that, we have to define two conventional things. One is air, another is water. Water is there because water is the moisture, right? So we have air, water. These are two conventional components, and we will have biomass. Obviously, biomass doesn't have any alias. We have to define it as non-conventional component. Okay. Now go to the methods and we will put it ideal property method. And you will find this NC props. This has become red. Okay. Because it needs some value. NC props means non-conventional properties. So just click it over here. So it is asking for the property models of non-conventional components. So we have learned various models. In the problem, they have said that use H-Col-Gen model and DNS-TY-Gen model. For density, they have asked you to select DNS-TY-Gen, and for enthalpy, we have to use H-Col-Gen model. So for enthalpy, we will use H-Col-Gen model. So there are other models also. You will find this is Col enthalpy model for Bowie correlation. Bowie correlation, you remember? I just discussed Bowie correlation, then Dulung's correlation, etc. So this is Bowie correlation. This is general enthalpy model, nth gen. This is tab poly model. Tab poly means you have a tabular data of polynomial function. I think I have discussed in some other lecture. And this is enthal user, that is user enthalpy model. Suppose you have done extensive research on that and you have generated some model of your own research. So that also you can provide over here. And other models you can just go through one by one and learn them. Now in this example, we'll use H-Col-Gen. The moment we choose H-Col-Gen, there are four options come over here. 1, 1, 1, 1. Now what are those four options? We go back to our help file and we can see them once again. So this is the H-Col-Gen model. This is 1, 1, 2, 3, and 4. And each one of them, we have to provide the data. So by default, in all the cases, the option codes of 1, 1, 1, 1 have been chosen. That means for heat of combustion, they have chosen Bowie correlation by default, Kirov correlation for heat capacity by default, and elements in their standard states at 298.15 K and 1 atmosphere, that is enthalpy basis, as 1. So all of the options code 1 has been chosen. Here it has been said default 1 for each option code. So everything 1 has been chosen. But in our case, we will not use the Bowie correlation because we already have the information of heat of combustion. We already have the information of heat of combustion, that is 17 megajoule per kg. So we will use 6 instead. User input value HComb. So in the first case, instead of the option code 1, we will put option code 6. And for density model, they have asked us to use DNS-TY-Gen model. This is DNS-TY-Gen. dchar, IGT, dcol IGT, we already have seen those model. And this is for tab poly and this is for user density model. Now, if you have done extensive research and got your own model of density that you can feed in, okay? But in this case, we will use DNS TYGen model. The moment we choose the DNS TYGen model and HColGen model, we find over here that required component attributes. That means these are the component attributes that are required for this particular method. Now for that, we have to enter the data. Now we already have the information on the heat of combustion and average density. For this particular two data, we assume that the agricultural biomass non-conventional component to be a pure component having this average density of 470 kg per meter cube and heat of combustion to be 17 megajoule per kg. So these two information we have to use as a pure component, not any kind of mixture at all. So we have to use new and put it non-conventional. Okay. So pure component non-conventional parameter, we have to find out the HComp, that is user input for heat combustion on a dry basis for coal or char in coal general enthalpy model HColGen. So we have to choose this and we have to provide the data in megajoule per kg, 17 megajoule per kg of heat of combustion. So this is megajoule per kg of biomass. The data is 17. Okay. So this is one information, and density information is also to be given. So the density information 470 kg per meter cube. So for that, we will add another pure component data for a non-conventional component. And here we have to use this one. Coefficients for the non-conventional general density model. So here the data is kg per meter cube of biomass, and this one is 470. Okay, so that's how you define your density of non-conventional solid component, right? So that's how you define everything in the property. Now you can run it. Okay, so the property method has run. Now we go to the simulation window. In the simulation window, we have to first go to the setup. In the setup, we have to define the moisture component first. So in our case, the moisture is water. So we define water over here as the moisture. And we have to define the PSD. So what are those PSD? We have how many intervals? We have 0 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 8, and 8 to 10. So we have 1, 2, 3, 4, 5, 6. So we have 6 such thing, and it is in millimeter, right? It is in millimeter. So 0 to 3, 3 to 4, 4 to 5, or am I doing any mistake? No, 4 to 5, then 5 to 6, then 6 to 8, and 8 to 10. Okay, so that's how we define the solid PSD. Now we go to the solid component, and from the menu we bring in the dryer. So this is our dryer, and we have to connect the material stream. So this is the feed stream, and its name is, let us say, wet biomass, and this is dry biomass, and we are drying it through air. So let us say dry air, and this is moist air, so we can say wet air. So dry air is supposed to collect the moisture from wet biomass, and it will exit from the top. Now let us first define dry air. So dry air enters at 200 degrees centigrade and 2 bar pressure. So it is 200 degrees centigrade and 2 bar pressure, and the flow rate has not been given, but let us take a guess. For instance, the flow rate of wet waste agricultural biomass is 20 tons per hour. So let us assume that we need at least 3 to 4 times air. Let us start with 3 times and then we will increase so that the drying can be done. So if it is 20 tons per hour, let us feed in 60 tons per hour. So 3 times. So it is 60 tons per hour. Okay, and the wet biomass. So wet biomass, you have to feed in the data, that is 25 degrees centigrade, 1 bar pressure and 20 tons per hour. So 25, 1. Okay, now it is not mixed, it should be NC solid, non-conventional solid. For that we have to define our stream. So our stream class is mixed NC-PSD, so non-conventional solid with particle size distribution. So if you choose this, then our option will be open for you. So now NC solid is open. Let us go to NC-PSD. The temperature is 25 degrees centigrade, pressure is 1 bar. Am I feeding in the correct data? Yeah, biomass enters at 25 degrees centigrade, 1 bar, and 20 tons per hour of. So it is 20 tons of solid. Now you see two things are open. They are red marked. We have to fill in the data. One is particle size distribution, another is the component attribute. Okay. Now let us first select the particle size distribution. Particle size distribution, we have 3 to 4 is 10%. So 3 to 4 is 10%. 4 to 5, 20, 20, 30, 20, 10. 20, 30, 20, 10. So 0.2, 0.3, 0.2 and 0.1. So 0 to 3 must be having 10% over here. So that makes our cumulative weight fraction to be 1. Okay. So that's how we define our particle size distribution. Now, for non-conventional solid, you have to have this component attribute. And in this component attribute, you have to provide the data on proximate analysis, ultimate analysis, sulfate analysis, and general analysis. Okay. Now, what are the proximate analysis? We have the data over here. We have 20% moisture content. So this needs to be given in wet basis and all other in dry basis. So fixed carbon is 13.11. So it is 13.11. Then volatile component should be 83.18. And ash content is 3.71. So it is 3.71. So that's how the proximate analysis is given. And the second thing is ultimate analysis. Ultimate analysis, you see, ash, carbon, hydrogen, nitrogen, chlorine, sulfur, oxygen, everything is given over here. What is ash content? 3.71. So we write 3.71. Carbon is 49.02, so it is 49.02. Then hydrogen 5.74. Then 0.71. Nitrogen 0.71. Chlorine 0.2. Sulfur 0.22. And oxygen 40.4. Okay, so if you add all of them, you will find 100%. Okay, so this is ultimate analysis. Now we have to do the sulfur analysis. Now we actually do not have any information on pyritic and organic. Okay, we know there are sulfur because we have got 0.22 sulfur over here, but we do not know in what form it is. Now let us assume that all the sulfur that we find in ultimate analysis, they belong to sulfate. As we do not have any information on that, okay, so we just put all the sulfur into sulfate only. Pyritic and organic, we leave it as 0. And finally, the general analysis. General analysis, we have 20 such options. Element 1, element 2, element 3 up to element 20. For instance, if you talk about biomass, it might have some algae, some food material, it may have some wood pulp, it may have some rotten leaves from trees. Okay, so they may be element 1, element 2, element 3, element 4, etc. So if you have such information, you can give that we have this much of percentage of wood pulp, this much of percentage of algae, this much percentage of food waste, etc., etc. But we do not have such generalized analysis. So we say that everything together, it is 100%. So element 1 is 100%. So that makes our wet biomass characterization attributes complete. So that's how we given the information of wet biomass and dry air. Obviously the dry air we started with 3 times and later we will see what we can do. Then we have to define the dryer. Okay. Dryer definition we have already learned before. The operation mode is continuous and dryer type, it is a convective dryer, right? We have seen over here, it is a convective dryer, which is 10 meter long and residence time of the biomass is 5 minutes. So we have solids residence time which is 5 minutes and the length of the dryer is 10 meter. Is it 10 meter? Yeah, it is 10 meter. And then the heat and mass transfer coefficient, I think this information is also there. Here we have heat and mass transfer coefficient. So this is specified mass transfer coefficient is 0.02 and heat transfer coefficient in kilowatt per meter square per Kelvin 50. So this is 50 kilowatt per meter square per Kelvin. So that's how mass transfer and heat transfer coefficients have been provided over here. Now go to the drying curve. So in the drying curve, we have to provide the critical solid moisture content. On the dry basis, it is 1.2. So leave it in dry and it is 1.2. And equilibrium solid moisture content 0.02 in dry basis. And normalized drying curve model, we do not have function, rather we have drying curve data. So we put data over here and these are the information we need: normalized solids moisture and normalized drying rate. So normalized moisture and normalized drying rate. So we shall provide the data over here. Let us write it down. So this is 0, this is 0.0678, 0.1525, then 0.2373, 0.3220, then 0.4068, 0.4915, 0.5763, 0.6610, sorry, it is 0.6610, then it is 0.7458, then it is 0.8305, then 0.9153, and finally 1. Okay, so this is the drying curve data and this is the drying rate. The first case it is 0.033, 0.1594, 0.3049, 0.4366, 0.5545, 0.6586, 0.7488, 0.8252, 0.8878, 0.9366, 0.9716, 0.9927. Oh, there is a mistake somewhere. This is 1. Let me check where I have missed out something. So 061525237332240668. Oh, I have jumped 2. Okay, so this should be 4068, then 4915, then 5763, then 0.6610, 0.7458, then 0.8305, then 0.9153, and finally 1. Now this must be correct. Okay. Okay. So all the information that is needed for this simulation, it is now given. Now let us run the system. Okay. It's taking a lot of time. I believe, yeah, it's error is being shown. So these are some warnings. So we do not bother about warning, but the error is vapor temperature reached upper flash limit during iteration. So the calculation of dryer stopped. So in my opinion, there might be some problem with the air flow rate. So a 3:1 ratio of air is to biomass may not be sufficient. Let us increase the dry air rate to say 4 times. So 4 into 20, it is 80. Okay. So air is to biomass 4:1. Let us try. This also is not converging. So let us increase some more. Instead of 4:1, let us try with 5:1. So 5 times. Yeah. Now the results are available and the simulation has run. So one thing is sure that air is to biomass mass ratio has to be between 4:1 to 5:1, some number we have to set. First of all, let us check the results. So these are the results of dryer. We can see the exhaust gas temperature. So exhaust gas temperature, that means the air which is going out. So air was entering at 200 degrees centigrade, but exhaust air is 54 degrees centigrade. And the solid residual time is 5 minutes. It should be 5 minutes, yes. Critical moisture content 1.2 and equilibrium moisture content. So initial solid moisture content is 0.25 on dry basis. Okay. So it was dry basis 0.25 and outlet solid moisture content is 0.02. Obviously it has reached the equilibrium moisture content. It cannot go beyond that. And overall evaporation rate in tons per hour, it should be 3.68 tons per hour. And what is the calculated duty? The calculated duty is 50 kilowatt. Now let us see the stream results. Here you can see the dry air is entering at 200 degrees centigrade, wet air is going out at 54 degrees centigrade. So there is a loss of 150 degrees centigrade temperature. That is quite usual. And wet biomass entering at 25 and it is almost reaching at 200 degrees centigrade. That is the dry air temperature. Obviously, this is in counter current fashion. So this is the flow. So one thing is over here. So this is one flow and this is another flow. So this is dry biomass. Dry biomass is going up to 199 from 25 and dry air, this is coming down from 200 degrees centigrade to 54 degrees centigrade. So that's how the system works. and the dry air had only 100 tons of air, but wet air is carrying 3.68 tons of water also, which has been taken from the biomass. Biomass originally had 20 tons of material and it has lost 3.68 tons and it is carrying only 16.32 tons in the outlet. Okay. So evaporation rate is 3.68 tons per hour of water. In this example, we have missed one thing, that is the heat loss. The heat loss of 100 kilowatt can be assumed. So that has been specified in the example. But while doing the calculation, we found that the heat loss over here is 50 kilowatt, almost the half. We cannot call it an error because it is calculated by Aspen. But how to fix it? How to fix it to be 100 kilowatt and then change our simulation accordingly. So it is possible that if we change the dry air flow rate to some extent, then the heat duty can be changed accordingly and it can be set to 100 kilo. Now you know how to use the design spec. In the design spec, you can define the heat duty as a target, and the target should be 100 kilowatt, and you can vary the dry air flow rate, and you can try to achieve that value of dry air flow rate, which will yield the calculated heat duty to be 100 kilowatt. Okay, so that's how you can solve that problem. Now I give it to you as a home task. With this, we come to the end of this lecture. I hope you have enjoyed it. We'll come back with yet another interesting lecture very soon. Thank you.